Hi folks, StylePoint here, and today I want to talk about two very important topics in computer science. These are the API design and numerical stability. And of course these topics or concepts, they're also very applicable to the kind of work that we're doing with the Implement series, where so far we have implemented 3 different machine learning models from scratch. And I want to delve into these topics by looking at the comment, or reading it, the comment made by one of our community members, one of the users. Let's see. So it's user Radu Grosu, the member of our community. He made 2 comments under the video, implement Gaussian naive Bayes. The first comment says, the API is unusual. There is no need to save the training data on the instance. Those should be arguments or formal parameters to the fit method rather than the init magic method. And of course, in this case, this was like the layout. This was the way our class was initialized. It would need features and labels. And so the suggestion is we should probably put them inside the fit method here to avoid like unnecessary maybe copying of data. Of course, the init method, we don't have it here, but it's implicit because data class kind of provides it to us. So there is an implicit init here that we don't see. Now, the second point, the second observation that Radu Grosu made, I think is even more important. So they point out that it's numerically more stable to use log likelihoods and sums instead of products. And I think it's especially important in case of the Gaussian naive Bayes, where we compute likelihood by multiplying all these different likelihoods computed using the Gaussian likelihood function. And so I think I made a huge mistake. It was a big blunder on my part, not mentioning this. I have not implemented it, of course. I mean, never mind implemented it properly. I didn't even mention this. And the proper implementation would use log likelihoods. Now, I'm going to go over, I'm not going to necessarily implement this now. Maybe I'm going to make a change in the repository. But I do want to talk about the API design, right? And then I'm going to talk about the numerical stability and some of the approaches to solving the issue with multiplying a lot of numbers, a lot of probabilities, a lot of numbers between 0 and 1. Okay, so we thank Radu Grosu and we go ahead and explore the code base here. Okay, this is, I think, the video we're recording right now. We don't really care about that. But we do care about the Gaussian naive Bayes. So this is actually the API that we had. We would have features, labels directly in the initializer of Gaussian naive Bayes. And then we would use like self.labels and self.features across the code base. Now the suggestion is to use features and labels directly in the fit, so pass them directly. That would mean, well, the self.labels, in this case, we would still need to initialize. The reason for that is that we use self.labels down here in the predict method, but at least we can get away with not using self.features. So get away with just providing features directly. So this way, we have features and labels passed directly to the fit method, and this basically allows us to just initialize only self-labels we store, allows us to get away with not initializing self.features, not writing self.features equals features, which would be written for us anyway because we're putting data class. Of course, the API here would change. So train, we would just provide them here, right? And then this is like the pyrite, which is like a code linter, it complains. And then we would be able to run it. There we go, and we would get the same result. Now, this issue with the API design, I think it's even more, even worse with the linear regression, where this is not actually the code that I had there. I think this is the code that I had. And of course, in this case, we would have to do self.features, and here we would have to do self.labels. And this is basically what we had in the video, right? We provide features and labels directly to the initializer, and then it works that way. But of course, this is not the best, I think, approach here, because there is nowhere really other than the fit method where we use these features and labels. And plus, we store these features and labels directly inside the linear regression. In case of Gaussian naive Bayes, we would have to store labels. We would still have to store them, but at least we would get rid of features. Here, we store both of them directly inside the class. And it can be kind of wasteful, right? Because features and labels, they're not very cheap to copy or cheap to store. When it comes to learning rate, epochs, and logging, these are like float, int, and bool, respectively. So floats, ints, and bools, they're, of course, a lot cheaper to store. Storing a learning rate, which is a single float, is a lot cheaper than storing features and labels. Both of them being NumPy arrays could potentially be huge. And so the suggestion is basically to store that way. So storing them this way is basically kind of wasteful, as opposed to the storing them this way. We don't really store them this way. We pass them directly to the fit method, and fit just uses like the shape of features to get number of samples and number of features, and then we do the gradient descent, and the predict does not even use the features and labels, as I said. So yeah, with the API design, the initializer is going to take things that are like parameters, hyperparameters, I think, for the ML models, DL models, AI models. That's kind of the approach we're going to take from now on. We're not going to put features and labels directly inside the model. I think even in the unsupervised learning models, we're going to follow this API where we initialize only the hyperparameters and maybe parameters like logging. And fit usually would take the features and labels, like maybe train, fit, something like that. That would be like the name of the method. And we do this, of course, because the types of these fields, like learning rate, epochs, logging, the types of these variables, these are cheap to copy, cheap to store. And I'm not going to go into like different types of floats like and ints, like int 16 and float 32 and float 16 and float 64 and so forth. But this is basically what I wanted to go over when it comes to API design. Okay, now we're going to get back to the Gaussian naive Bayes, and we're going to talk about the numerical stability, especially in the context of this model. Now, the user rightfully pointed out that the likelihood, what we're doing here with the likelihood and prior, and then we're multiplying these two numbers, both of which would be between 0 and 1, is that we're pretty much asking for some numerical instability problems. So the likelihood itself is the product of these likelihoods that are computed using the Gaussian likelihood function defined here. So we pass data, mean variance, it gives us a number between 0 and 1. And what we do is that we multiply these numbers. And we have a bunch of numbers between 0 and 1. We multiply them, and we can potentially run into a numerical instability problem. And the prior, of course, is also between 0 and 1. And then we multiply something by something that is two things that are... So likelihood is already like doing very bad because it's multiplication of many numbers that are from 0 to 1. But then we also multiply that by prior, that is making it even smaller. So how can we solve this? So let's look at the some of the approaches that we could take here. And I'm going to discuss one approach, which is, I think, pretty much like the correct approach here. Let's have like a x, make it like 0.001. X is like maybe like a probability. And let's import math, okay? And what we're doing in Gaussian naive Bayes is that we're multiplying these probabilities. Now, I'm going to assume all of the probabilities are x. And so in this case, we multiply maybe 100 of these x's or maybe 10 of these x's. And if we multiply 10 of these x's, we already get like 10 to the power of minus 40, like e to the minus 40. Okay, so we still have some, numerical instability here, but that's what we get. Okay, at least we can compute it. Now, if we make it 100, we already run out of precision, basically. We're having problems here. The way to solve this, basically, is to use the log scale. Otherwise, of course, if we have numbers between 0 and 1, at some point, if we have enough of them, if we multiply them, we're going to get numbers smaller and smaller and smaller and smaller. Even if x was something like 0.9, this product is already goes to like minus 5. And of course, if we increase it to 1,000, it's minus 46. Okay, so very quickly, we're running into these numerical problems, numerical stability problems. And so how can we solve this problem? Like, what is the approach for dealing with this issue of numerical stability? Well, the way we're going to solve it is using one of the most beautiful functions in all of computer science and mathematics. The name of the function is logarithm. So basically the log function. But before we jump into that, let us first examine what we already have. We have x, which is the likelihood, and we have this chain of multiplications where we multiply x onto itself 100 times. And we get 0 back because, of course, the code itself is numerically unstable, which means that we have effectively run out of the precision. Now let's take a look at the log function. What happens when we give it x as an input? Well, if the input is between 0 and 1, it maps that input to a negative number pretty much. But in general, what the log function does is that it maps input onto what's known as the log space or the log scale. And the properties of the space are so cool that I think that alone, the fact that log function maps input onto the log scale, qualifies log function to be one of the most awesome functions in all of computing. But in this case, in case of the Gaussian naive Bayes model, where the problem that we're having here is that we have to multiply these small probability values, small likelihoods, all of them being between 0 and 1, without running into numerical stability issues. And so to solve that problem, logarithm says, I got something for you. I got this really cool decomposition rule where the multiplication of the logarithm of the multiplication is the sum of logarithms, right? We can decompose logarithm of x times x as the logarithm of x plus the logarithm of x. And it's a very general rule. It does not have to be the same x multiplied onto itself. It can be logarithm a times b times c, and that will decompose into a logarithm of a plus logarithm of b plus logarithm of c. So to kind of check this here as well, there we have it. Math.log of x times x is the same as math.log of x plus math.log of x, the same values. Now, how can we convert? How can we basically speak logarithm? How can we translate math.prod into this language of logarithms? Well, as is, of course, that's going to give us 0. But what we can do is that we can say this multiplication of x's, instead of multiplying them directly, we're going to find the log of this multiplication. But of course, this expression here, it would still result in numerical errors. It would still be numerically unstable because we're still multiplying these x's. So this would be evaluated first, and then it would evaluate math.log. But we're not going to do this. What we're going to do is that we're going to decompose it into the sum of logs. So let's comment this out. And this is basically the approach that we're going to take. So math.prod, we're going to convert that into a sum of the logs. And there we have it. Minus 921.0340371 and so forth. But we got a reasonable number. We didn't get 0. There's no numerical instability. And of course, we got a negative number because in that interval 0, 1, we're pretty much adding up negative numbers. But how stable are we? Like, can we go higher than 100? Can we go as far as 1,000,000? How stable are we? Well, we are very stable. I mean, that's minus 9,210,340 point something, but no problems, right? We could still get a number. Now, before we spoke logarithm, we couldn't even operate on a scale of 100. Now that we speak logarithm, we can operate on the scale of 1,000,000, and we can probably go further than that as well. But now, let us actually fix the problem with the Gaussian naive Bayes implementation. And before I'm going to do that, let us first save the results, save the metrics, so that we can basically use these metrics as a reference. So once we make the changes, we want to make sure we have the same results here. Okay, the first change, and all of the changes are going to be inside this predict method. The first change I'm going to make is, this change right here. I'm not sure why we're converting prediction into the NumPy array, because it's already a NumPy array. So I think there was a little typo there. So prior, we convert that, we map that onto the log scale. We apply log onto it. The next thing, maybe we can make it more readable. So we can call this pairs, in pairs. And of course, this is going to be the kind of the same approach. It's going to be a sum of log likelihoods instead of operating on the like a likelihood kind of a scale, like the actual, I think, default scale. We operate on the log scale, log likelihood basically. And here we also need to do addition because both prior and likelihood are going to be on the log scale. So we do addition there as well. And there we go. We have these results, and let's copy these over here. So 0.947, 0.947, 0.961, 0.961, 0.944, 0.944, 0.949, 0.949, 4 out of 75, 4 out of 75. So yeah, once again, we can take a look at these results. That's the same. So that's going to be it for this video. We have discussed the API kind of that we're going to be using moving forward for the AI ML models. We have also discussed numerical stability and the issues that may arise when we multiply small numbers. We have discussed this in the context of the Gaussian naive Bayes. We have fixed the issues that we had in our implementation. And it's especially cool that we discussed it in this video, because the next video, we're going to be implementing the logistic regression model from scratch. And in that model, we're going to be meeting this activation function called sigmoid, where if we implement that function like naively, like in a naive way, in like a common sense way, we're going to run into a numerical stability issues. So we're going to have to like notice that there's something going on there, and whatever's going on is not good, and we're going to have to fix it. And so now that we understand what's numerical instability and, well, what that basically is, like overflows and underflows and things like that, you know, precision errors, we're going to be able to, I think, successfully, you know, overcome that problem of, you know, having the sigmoid being, having sigmoid mess up the results because it's numerically unstable, and fixing that problem. So thanks a lot. If you have any questions or suggestions, please feel free to comment in the comment section. I'm going to try to answer or respond to all of the questions and take into account all of the suggestions. And I'm going to see you in the next video, which is going to be about the logistic regression. We're going to be implementing it from scratch.